The first thing to understand about the alkali metal water reaction is that they're metastable. That is, sometimes they'll just fizz away happily, and sometimes they will explode. The critical bit here is this is a macroscopically heterogeneous reaction, and those never explode. Indeed, they can't, but this one does. So in order to get an explosion out of a heterogeneous reaction, you need the reaction that consumes part of the surface to generate at least that much more new surface. That's just the criticality requirement for a heterogeneous reaction to yield an explosion. So this is the thing. When alkali metals react with water on the surface, they produce hydrogen, maybe steam, and the alkali metal hydroxide, all of which will serve to keep the reagents apart, and none of them will serve to generate new surface. That is, this reaction is expected to inhibit further reaction and hence quench any possible explosion. Now, through much experimentation, we eventually worked out that this explosion was very critical on having a clean metal surface impacting on water. Now, sodium-potassium alloy, it turns out, is a liquid and very easy to handle in syringes, so you can generate very good surfaces under argon. And thus was the kit born, where a fresh drop of sodium-potassium alloy falls through 1 meter of an argon atmosphere and impacts on the water surface. And this results in an explosion essentially 100% of the time in less than a millisecond. Indeed, just to see what was going on here, we needed to employ some top-shelf high-speed cameras, recording at least 10,000 frames per second. So here we have a frame-by-frame comparison of a drop of water hitting the water surface on the right, compared with the sodium-potassium alloy drop hitting the water under the same circumstances. So for the first 0.3 milliseconds of the sodium-potassium alloy hitting the water is characterized by these peculiar patterns that are just not typical of one drop of liquid hitting a water surface. However, the key event happens 0.4 milliseconds after impact, where these metal fingers shoot out of the metal. The impact speed is about 5 meters per second, and these spikes have achieved about 5 times that velocity in 1/10,000th of a second. An acceleration of getting on for 30,000 meters per second squared, and if that acceleration was maintained for just 1 second, that would easily give you escape velocity from the Earth. So what could possibly be causing that? What could possibly be causing the metal to accelerate into the water like that? Well, all of the conventional explanations involve gaseous expansion of one form or another. However, that's clearly not what's happening here. These metal fingers are injecting themselves into the water before there is any obvious gas production. And obviously, if there is no obvious gas production, this couldn't be something like the hydrogen burning on twofolds. First of all, you can see there is no gas being produced yet. And secondly, this is conducted under argon, so there is no oxygen for the hydrogen to burn in. Well, once one looks on the microscopic picture, the potential driving forces become very limited. Maybe the most obvious one is that the conduction band electrons migrate into the water very quickly, but this will create a lateral repulsion on the surface of the metal, and if that lateral repulsive coulombic force becomes equal to the surface tension, then it is now energetically favorable for the metal to increase its surface area, and that's the core critical requirement for an explosion out of a heterogeneous reaction. Now, large-scale quantum calculations are prohibitively expensive, but we've conducted many smaller calculations on 7 to 19 either sodium or potassium atoms. The transfer of the electrons to the water is indeed almost instantaneous. It takes about a picosecond and results in the fragmentation of the sodium atoms at about the speed of sound, about 300 meters per second, and considerably faster than the 30 or so meters per second of our macroscopic spikes. But the point is nonetheless made that the repulsive forces here are on the right order of magnitude. This charge separation in quantum mechanics can be transferred to force field molecular dynamics simulations by placing alkali metal cations on an alkali metal drop in water. Here it was found that at higher charge loadings of about 50%, that again the speed of the explosion was comparable to the speed of sound. Further, when some hydroxide counterions were added to this just outside of the cations on the surface, again a strong expansion was found, although now it was about an order of magnitude lower. Now, with electrospray, the electrostatic charge buildup on the surface eventually results in the formation of Taylor cones. And these Taylor cones do bear a similarity to the spikes observed when the metal injects itself into the water. While the process here is not directly analogous to the macroscopic charge separation in electrospray, in fact it's actually more of a strong and very short-lived zeta potential. The bottom line is, when these coulombic repulsive forces on the surface become equal to the surface tension, they can fulfill the criticality requirement for a coulombically driven heterogeneous explosion.